Welcome back, and let's start talking about Newton's second law of motion. Newton's second law is best described using the mathematical formula F is equal to ma. Here, when we talk about F, we are talking about the net force acting on an object. Okay, so this is the overall force that is applied to an object. And of course, m, as always in science, stands for mass. And the mass here will have a unit of kilograms. We need to make sure that our mass is converted to kilograms in order for this equation to work correctly. And of course, our force is measured in newtons. Remembering units are very important when we're doing calculations in science. And of course, acceleration, we should remember from motion, has units of velocity squared. And in this case, it will be meters per second squared. Or you may have seen it written as meters per second squared or meters per second per second. These are all exactly the same quantity. They all mean meters per second squared. We just have different ways to write them. But what this equation is telling us is that when an unbalanced force, i.e. a net force greater than zero, is acting on a mass, it will cause an acceleration. It will change the mass's motion and cause it to accelerate. So we can use, if you're still feeling a little uncertain about how to rearrange these formulas, because you will need to be able to rearrange them in order to do the calculations, I've provided the triangle here, remembering you can place your thumb over the one that you're looking for when you draw this out, and this means that the mass will be equal to the force divided by acceleration. If we want to find acceleration, then we place our finger over the A, and what's left is the calculation that we do, force divided by mass. Hopefully, though, you're getting better at rearranging these on your own without using the triangle. So just a little bit of review on what acceleration is from our motion unit. And we should remember that acceleration is the change in an object's velocity with a change in time. Okay, so essentially this means that if we have a positive acceleration, then we will have an object speeding up. If we have a negative value for the acceleration, then our object will be slowing down. If the acceleration is zero, then we have no change in the acceleration, so the object will be traveling with a constant velocity. Okay, and we can substitute in, remember, capital delta here means change. So that means we're looking at the final velocity, final minus the initial velocity all over the final time minus initial time. And you, of course, will have these equations given to you for the exam and for the test. Okay, so our change in velocity divided by our change in time is equal to the acceleration. So if something is happening over a short period of time, we will have a high acceleration. If it occurs over a long period of time, we have a small acceleration. Okay, and this is also remembering that velocity is a vector quantity, so direction is critical. So positive direction for acceleration is speeding up, and a negative value for acceleration is slowing down. Okay, so what does this all mean for Newton's law? What it's telling us is that Newton's second law is saying that if the mass of an object is the same, if I give it a bigger force, then it will accelerate at a greater rate. Its acceleration will be larger. And this makes sense. If I take a small car with a standard engine and add a driving force to that, it will accelerate at a slower rate than if I have the same car with a larger engine. Okay. Or if I have an empty shopping trolley, then if I give it a small push, it will accelerate slowly. If I give it a large push, it will accelerate more quickly. So that's the first part. If I keep the mass the same, then to have a bigger acceleration, I need a bigger force. So this means that the force and the acceleration are proportional. They're directly proportional. if I increase the force, I'll increase the acceleration. But if we change the situation around, and this is what we're seeing in this animated GIF here, if I have a larger mass, then for the same amount of force, I'll get a smaller acceleration. So if I have a smaller acceleration for a larger force, this means they're inversely proportional. And we can see that in that the small child here being pushed accelerates with a greater velocity, giving a larger swing than the larger person on the swing for the same force. So the first situation is where we have constant mass. The second situation is where we have a constant force. So let's look at how this plays out, because most of these are going to be seen in calculations. So in order to see the second law at work, it's helpful for us to use the formula by substituting in values. So if we consider the first situation, if the person that we see here, we have a trolley with a small mass applied. So the person pulling the trolley, okay, will get a greater acceleration compared to if they tried to pull a trolley with a larger mass. And we can show that mathematically by substituting in a few different values. So if in the first situation, we consider that the person applies a force of 15 newtons, so we're going to say that this force is 15 newtons, and this is the net force, okay? And the mass of the parcel is 5 kilograms. I can calculate the overall acceleration by placing it into our F is equal to ma formula. I want to find A, so I'm going to divide both sides by m, so I'm going to get F divided by m. This means I'm going to take my 15 Newton force and I'm going to divide by my 5 kilogram mass, and I will discover that I will get an acceleration of 3 meters per second. Okay, we're going 3 meters per second squared. Okay, will be my acceleration. So this means that for every meter traveled, my speed is going to increase by 3 meters per second. So after the first second, I'll be traveling at 3 meters per second. After 2 seconds, we'll be traveling at a faster speed again, okay? So in the second situation, now the mass of the parcel is going to be 25 kilograms. So we can see that we have increased the mass of the parcel, okay? But the force is remaining the same. So our net force is going to be 15 newtons. I can do exactly the same thing as we did before. We're going to work out the acceleration. So we're going to have the force divided by the mass. So now we have 15, and instead of being divided by 5 in terms of our mass, it's actually going to be divided by 25. So let's do that calculation. So when we do this calculation, we will get 0.6, and remembering our units of acceleration are meters per second squared. So we can see here that we will have a much smaller acceleration for the same force, and that makes sense. If we are pulling with the same amount of force, it's going to take more time to get that larger mass up to speed. We see that when we look at the way that vehicles move as well. So if we consider a train, if we have 2 carriages, we have a large force pulling a load. If it's only carrying a single trolley of load, then we're going to have a large acceleration. This train is going to be able to start its motion and then accelerate quite quickly while that force is being applied. If we take it down to 1 trolley, we're going to 1 engine and 1 trolley, we're going to have half the force. So now this is going to halve our acceleration that we're able to attain. If I want to increase the amount of mass and maintain the same acceleration as in the second example, I would need to increase the force. So in this case, I've increased the force and increased the mass. So now we would have a similar acceleration as what we saw in the one where we had 1 trolley and 1 engine. Then we can have the situation where we have double the mass and 1 engine. This would drastically reduce the acceleration that we see. It will take a lot more time in order for this trolley and engine to reach the same speed as the one that was pulling with more force. Okay, so remembering that acceleration and speed are different. This is the rate at which the speed is changing. So if all these four situations were trying to reach a speed of 100 kilometers per hour, then this one here would take the longest to get up to speed because it has the least amount of force and the greatest amount of mass. Okay, so its acceleration will be slower, so it will have a slower change of velocity over time. Let's have a look at a couple more sample calculations. This is one from our booklet, and let's have a look. We've been told we have a car with a mass of 1,200 kilograms and it's traveling along a road. The motor supplies a force of 2,000 newtons, so this is its driving force, to push the car forward, and there is a frictional force totaling 1,500 newtons. Okay, so we have a force of friction, and it's acting the opposite direction. With physics problems, it's always a really good idea to draw yourself a diagram. So I'm just using a rectangle to represent the car. I have a driving force, we were told, of 2,000 newtons, and that's my driving force. I have a friction force, okay, force of friction or drag, that is equal to 1,500 newtons, okay, and I have a mass of 1,200 kilograms. This now allows me to see what's going on, and I can see that the vector of the driving force is larger than the friction force, but I need to calculate my overall net force. So this is what part A is asking us to do. The resultant force is the net force acting on the car. So we have 2,000 newtons in the positive direction of movement, and then we have 1,500 newtons in the opposite direction. So we're going to subtract it. This gives us a total net force of 500 newtons. I can now work out the acceleration of the car using F is equal to ma. I'm going to rearrange to find A. So I'm going to have A is equal to F divided by m. My force is 500 because that was the net force acting, dividing by the 1,200 kilograms on the car. This will now let us work out 500 divided by 1,200, and that gives us an acceleration of 0.4167 meters per second squared. Okay, so this, and then the last question asks us to describe what this means with respect to the motion of the car. So we know that we have a positive acceleration, so we can state that the car will be increasing its velocity at an acceleration of 0.4167 meters per second squared. So for every second, it's going to be increasing this velocity with which it is traveling, and it will be maintaining the direction of original travel. So let's have a look at another one. This time we're told that a 0.1 kilogram stone is dropped from a cliff top, and if gravity on the Earth accelerates objects at 10 meters per second squared. This is an acceleration because gravity is an acceleration, and force due to gravity is the result of F equals ma, where we're using gravity as our acceleration. Okay, so first things first, diagram. We're going to drop a stone. It's got Fg working on it, and of course we would have air resistance. If it is falling, we know that the net force due to gravity is greater than the air resistance. So what is the downward force on the stone due to gravity? So we're looking for the force due to gravity is going to be the mass, 0.1, multiplied by its acceleration, which is 10 meters per second squared. So the downward force is going to be 1 Newton, okay, due to gravity. We're told the stone reaches terminal velocity, remembering this is a constant velocity, so it has steady speed. How big is the force of air resistance acting on the stone? So at constant speed or constant velocity, we know that the forces must be balanced. This means that the force due to gravity must equal the force due to air resistance. The force due to gravity isn't going to change because I haven't changed my mass, and the acceleration due to gravity is constant. So this means that the air resistance acting on the stone, air resistance must equal the force due to gravity, so this will be 1 Newton. So this is combining our knowledge of the first law with second law. Okay, so now we've been given a car with a mass of 1,600 kilograms and an acceleration, with a truck with a mass of 3,600 kilograms and an acceleration of 0.28. So let's have a look at this. This is very similar to what you see where cars try and avoid ending up behind trucks at traffic lights, and this will show you why. If we have a look to calculate the force required to get each vehicle moving once the lights turn green. So for the car, we know that force is going to equal mass times acceleration. So we're just going to substitute from our question. So we'll get 1,600 multiplied by 0.82. So if we do that on our calculator, 1,600 multiplied 0.82, this means that we will see a force of 1,312 newtons required in order to get the car moving. In the case of the truck, the driving force required is going to be 36,000 multiplied by 0.28. We can see that for the larger mass, the engine is going to provide less acceleration. So we have 36,000, and now we're going to multiply that by 0.28, and we're going to see that we will end up with 0.28. We would need 10,080 newtons. So it's going to take, if we consider that maybe we're going to have engines of the same size, or the engines are producing the same amount of thrust here, it would take the car a lot less time to generate that amount of newtons from its engine than it will take the truck. So the car will be able to accelerate away from the lights at a much faster rate. Okay, just a quick note on what time does to the impact of our forces. If we consider that we have been told that we have the net force is equal to the mass times the acceleration, and we know that the acceleration is equal to the change in velocity over time, we can actually combine these two equations and end up with this one here. So this means that if I increase the amount of time that my force is acting over, or the acceleration is occurring over, it is going to change the force. In the case of a deceleration, where I have a negative value, okay, where my velocity is changing in a negative direction, it's going down, this means that I will drastically reduce the amount of force that is being felt in the final impact. So we can see this in a number of ways where we try and prevent injury in sports or stunts. So if we provide a greater distance, i.e. more travel time over which the deceleration can occur, then we're going to see less impact force. We can see this when athletes, if they're jumping, or gymnasts, will bend their knees to absorb some of that force as they land. the use of pads such as cricket pads and cricket gloves in order to reduce the overall impact force of the ball as it hits. And of course, the use of large airbags and so forth for stunt men in movies so that they gradually fall into the bag, slowing their rate of acceleration before the final impact. Okay, so by increasing the distance the deceleration occurs over, it reduces the final force or the final impact. And that is it for Newton's second law.